Oh, he's group 9. I'm group 5. Who would I work with now? The fuck? Yeah.
All right. Bismillahirrahmanirrahim. Assalamualaikum. Good afternoon, everyone. So at the moment, I have afternoon. Assalamualaikum semua.
Good afternoon, Dr.
Good afternoon, Doctor.
All right. So before we start, your attendance will be on Spectrum. So I've shared uh, um, the password in the chat. So please remember to sign your attendance before the class ends. All right. All right. Okay. Um, all right. So I think we can start now. I think that I should start my recording as well. All right. Okay, so again, Assalamualaikum, good afternoon, everyone. So this is WIA 205 Algorithm Design and Analysis class. So my name is Asmiza. So I'll be handling lecture 1 as well as tutorial group 1, 2, and 3. Okay, for this semester's WIA 205 course. All right. So I guess for this course, as you all know, there are 3 lecturers that are handling this course. Other than me, we have the coordinator of the course, which is Dr. Hazrina, as well as Dr. Raja Jamila. So for my lecture group, I think 2 of the group, I think group 4 and group 5 will be under Dr. Raja Jamila for your tutorial. Okay, so so before that, how are you all? Are you good?
Yes, very good. Very excited.
Okay.
Okay. All right. So I just want to ask you, do you have any classes before this class? Because I know our class is like towards the end of the day, so I had a feeling that every time that we're going to have a lecture, your battery maybe like only left like around 50%, 40%. So do you have class right before this class?
Yes.
So do you have a break before this class, or you came straight from the class before?
We do get a break.
Break.
Yeah,
We
okay.
have
Okay, good. So I can suggest you to please have your lunch before you go into this class, because you need it in a sense, because this class is like there will be a lot of practical, like you need to actually pay attention a little bit more, because there's a lot of information that you need to take in this course. Okay. All right. So I guess it's normal that I start off this class by explaining to you what are the learning outcomes, what is expected out from this course. Okay. So basically, the learning outcome for this course is that by end of this course, hopefully by end of week 14, you should be able to indicate major algorithms and data structures, describe the importance of algorithmic design paradigms. So we're going to be looking at several algorithm design paradigms in this course, as well as being able to report in terms of the performance of the algorithm. All right. So the course overview, of course, if you have read this course will introduce you to how you can do analysis and design of computer algorithms. So you will learn basic design techniques, okay, important classical algorithms, advanced data structure and implementation in modern programming environment. Okay, so basically what you're going to be looking at is that what are how you can actually create an efficient procedures, okay, by doing algorithm design as well as the analysis. And then we're going to be looking at the scalability of the algorithm in terms of in relates to the size of input that you'll be feeding it into your algorithm. We're going to be looking at some of the data structures. I think some of the data structures you have seen it before in your data structure class, so something like Q. But we're not going to be looking at Q in specific, but in one of the algorithm, you will be using Q for it, okay? And then you're going to be learning new data structures as well. And then in terms of implementation for this course, we're going to be using Python. Okay, so I believe that in your previously you are using in your first year you are doing programming in Java, right? How about software modeling? Did you use any programming language when you do software modeling? Huh?
No, just UML.
Just UML.
Yeah.
So you haven't used Python before?
No.
No, not in any course. Okay. So basically, in this course, we will be using Python. Okay. There is a reason why we choose Python language, but I'm going to explain to you later. Okay, so basically these are the lecture topics. So we're going to be covering like 13 topics. Hopefully we can finish it, because from my experience, normally we will have to cut short some of the algorithm due to the time, and then because there's a lot of things that we need to practice in order for you to get to grasp, okay, in terms of how the algorithm works. Okay, so we have 13 topics. So these are the topics. We have introduction to the algorithm. We're going to be looking at sorting algorithms, string matching, divide and conquer, probabilistic analysis, randomized algorithm, order statistics. So we're going to be looking at specifically at two advanced data structure, which is hash and binary search tree. We're going to be looking at greedy algorithm, graph algorithm, dynamic programming, multi-threaded algorithm, and maybe in week 13. Normally, this week 13 we're going to start having our group presentation already. But at the same time, we will try to have a look at some like other algorithms that we can read from maybe perhaps an article. Okay, so that will be in lecture 13 and week 13, and in week 14 will be your presentation. Okay, so these are the references that we're going to be using. The lecture notes mainly is referring to this book, okay, by Common. So I think in the spectrum we have given you. I think it's on Spectrum. You're not supposed to. This is some like an unofficial copy, but you can use it for your reference. So our lecture notes mostly will be referring to these books. Okay, and then we are using other books as well, but this will be our main reference. All right, and then all right. So in terms of the platform that we use, of course, any information, material, you can get it from Spectrum. That will be our main place to get materials. And specifically for my lecture, if you can see inside the Spectrum, you will see there's a link to a Google Drive. So I will upload the latest lecture notes there before the class, or maybe a few days before the class. Okay, and as I mentioned, for this course, we're going to be using Python. PyCharm is not necessarily we're going to be use the IDE, the PyCharm IDE. But if you are in the lab, so we have PyCharm installed in the lab. So it's up to you to use any Python IDE. But I would recommend you to use PyCharm, okay, for the implementation. All right, so as you all know, our timetable, our lecture will be today 3 to 5. So Microsoft Teams will be the main place the place that we're going to do our lecture. So I hope everyone have how do you call that sign up into this team group. Okay. And then for the tutorial and lab, so for those, I believe you, all of you here in lecture 1 would be from tutorial group 1, 2, 3, 4, 5, yes? And I believe the rest 6, 7, 8, 9, 10 would be in lecture 2. And I will be handling tutorial 1, 2, and 3. And then Dr. Raja Jamila will be handling tutorial 4 and tutorial 5. All right. So actually, I need to talk to you a little bit about the tutorial group. But then I will address. I will talk about it later. I will just continue the lecture first. All right. So again, for those of you who are under my tutorial group, we will have our tutorial meet on the same team. Okay. But then I will create another channel for your tutorial group. All right. So assessment. For this course, the continuous assessment is 70%. Okay, so and the final exam or the alternative assessment will be 30%. Okay, so for the continuous assessment, we're going to have live online lab viva. So basically, you're going to implement your lab, and then we're going to have like a group viva. That carries 50% of your continuous assessment. And then you're going to have your group project, which carries 35%, as well as a live online test. Okay, so this is basically your mid-sem, which carries 20%. Okay, so that will make up to 70% of your continuous assessment. And you're going to have 30% of alternative assessment, where you're going to have a written assignment as well as implementation. So this is actually a group work as well. The details we will be letting you know once we publish the description. Okay, so I think it's not week 17. We plan to give it to you earlier so that you will have more time to actually do this. Okay. So tips in order for you to pass this course, basically your attendance. Please make sure you remember to mark your attendance on Spectrum. Password I'll be giving it to you before the class. Please try to participate in class activity, because like later on you're gonna see that there will be a lot of like step by step thing that we're gonna do in class. So I would really hope that you help me, do together with me, together with me in order, like to run through the algorithm maybe later on. So please participate in any class activity that we're going to have. Really work on your tutorial and lab, because that is where you will practice and you will see whether you totally understand the concept or not. Okay, the thing that we learned in the lecture. Please focus on your continuous assessment seriously, because 70%. So that you can pass. Like make sure that you complete all the continuous assessment. And I'm not sure, like whether people have told you or not, but some of the feedback that I have been told, that they said the algorithm is very difficult. Okay, this course is very difficult. So for those of you who find themselves, got stuck or anything, please don't stress. Please don't keep quiet. Please come to me, because for me myself, my student, if you have any problem, if you come to me early, I can help. So if you are like last minute, maybe in week 13, week 12, you come to me, you say you don't understand, since lecture 1 is very difficult for me to help. Okay, so come to me as soon as possible once you feel like yourself is lagging behind. Okay, and please have fun. Actually, algorithm is fun. Like you can once you get the hang of it, it is actually fun. All right. Okay. So, do you have any question?
Question. So, how do I get in contact with you if I have questions like off time?
Okay. So for me, actually the Telegram channel, You can either send me Telegram or email, okay? Or you can also text me through Teams. I'm available on those 3 channels.
Okay.
All right?
Eh?
Okay. And then I have like this is basically the not the second sem, the third sem that we are doing this online, right? Maybe perhaps we can try to get people to switch on their camera for once. I know some of you have the how do you call that, the facility that can support on the camera. So like why not we try like to mimic seeing people. We go to class and we see people. So I would totally recommend you to switch on your camera during class. Okay, so at least I don't feel like I'm talking to myself. It's so boring, like looking at the screen. I'm not sure whether you understand or not. All right. So is that all right? So maybe we can start next class. Hopefully more people can switch on their camera. I saw one Muhammad. I cannot see. Yeah, hello. Yeah, I can see him like switching on. Good. All right. So yeah. So basically that is the what? Any more question before we go to the first lecture? Class?
Dr.
Yes.
To how many people in the group?
How many people in the group? Normally it will be 6. 6 people in a group. Yeah, 6 people in a group. But I think for the tutorial group, I have 35. So maybe 6 in a group. We will try to have 5 to 6 in a group for the group project. Okay.
All right.
All right. So yeah, okay. I have some notes here regarding mathematical preliminary. Okay. So normally, previously we will have like a go through the mathematical preliminary that we use in this course. Okay, so basically it's just like a refresher. I'm sure you have seen it before, the logarithm, the summation, and so on and so forth. So I hope that you make an effort to go through the mathematical preliminary material, because we will be using it quite often in this course. Okay, when we do analysis, we are going to use a lot of mathematical equation in order for us to analyze the algorithm. So please make sure that you go through the mathematical preliminary. And I think for tutorial 1, I believe it is tutorial 1, or is that's a question. I will check back on Spectrum. There's a list of questions that you can actually try out whether you can actually do the mathematical the basic of mathematics or not. Okay. And then in regards to the tutorial group, I have a request from Dr. Raja actually, because for tutorial group 4 and tutorial group 5, there's only a few students. Okay, so there's a request by Dr. Raja to change the tutorial group with tutorial group 2. So I want you to give me some feedback if it is okay with you. I will exchange the tutorial group. I think it was 2 with tutorial group 2 with tutorial group 4. So we're going to exchange the class. So Dr. Raja is going to take tutorial group 2, and I'm going to be taking tutorial group 4. So let me know if you have any problem. This is just what I'm just going to ask you. So but then there's a request for that. Let me know if it is okay with you. All right. Okay. All right. Okay. So I hope you have no more questions. Let's go to our first lecture, which is the introduction to algorithm design and analysis. Okay. Group T5, I think it should be the same, because I think she requested another group with Dr. Hazrina as well. But I think T5 is still with her. I think T5 is with Dr. Raja. But I need to check whether I'm going to be exchanging with T4 or T5. Okay? I will update with you later, and maybe I'll post it in Telegram or something. Okay, to let you know. Okay. all right. No more questions. So let's just dive straight into what we go to our first lecture. Okay, so today we're gonna try and see what are the concept of algorithm, and then basically understand what does it mean by time complexity. And I think towards the end of this lecture, I don't know whether we can actually cover that. Normally, it will take some time for me to actually reach there. So if we have time, we're going to cover straight away into the looking into the running time complexity of iterative algorithm. Else, we're going to be pushing it to next week. So we're going to combine it with the recursive algorithm as well. Okay, so basically that is what we're going to be looking at today. All right. So yeah, so as you can see on the slide, so perhaps I would like to hear from you. What do like whenever you heard about algorithm, what comes into your mind? Class?
Process.
Process?
A mathematical equation that makes the device run.
Mathematical equation. Okay. So that's interesting because there's a little bit different between mathematical equation and algorithm. Because when you talk about equation is just like mathematical statement, but algorithm is more towards like having steps for you to go through in order to complete or to compute something. Okay, calculation. Sheridan said calculations. Algorithm, yeah, you can have a process to calculate something. Yeah, steps to solve a problem. Yeah. So normally when you talk about algorithm, it always talks about what are the steps, what are the process, what are the procedure. Yeah, generalized procedure in order for you to solve a problem. Okay. So if you look at the definition here, so algorithm is any well-defined computational procedure that will take in some values, either like inputs, and then it will produce some kind of output. Okay. And so basically, we can say that algorithm is actually a tool for solving some specific computational problem. Okay, so normally we will have algorithm that will solve a generic problem where like it will give you steps on how you can actually solve that problem, right? All right, so why do you need to study algorithm? So as you can see here, algorithm is everywhere. Okay, so they, like whatever technology that we have currently will use some kind of algorithm. And normally, like we always look for the best algorithm in order for us to implement all this technology. Okay, so we have the internet, web search, packet routing, even not just in computing technology. We also use we also have algorithm used in biology, like looking at the human genome project, protein folding, computers, of course, and it's not just software. You can also like apply algorithm or use algorithm when you do circuit layout, file system compilers, computer graphics, okay, movies, video games, security. All right, so we have in multimedia as well, social network, physics. So all this domain is not just software engineering domain. We apply some kind of algorithm. Okay, so in a sense, learning algorithm is not just benefit for computing or for software engineering or for computer science. It also benefits other domain as well. Okay, as you can see in these slides. All right. And then I believe for those of you who are familiar with programming competition, so normally the question that they have in programming competition, they will get it from algorithm courses. Like the things that you learn in algorithm courses. The solution to the programming competition, normally you will learn it in algorithm course. Okay, so for those of you who are how do you call that like to go to programming competition, so this is something that will help you perform better in those competition, learning about algorithm. All right. So other than that, the reason why you need to study algorithm is because the algorithm will help you understand scalability. Okay, scalability in this sense is like it is in the sense of how the performance grow in regards to the number of inputs. Okay, so we will look at the scalability in terms of that, and then you're going to see through algorithm, you will also should be able to see what is feasible and what is impossible, because from there you can see that whether you can achieve that performance or whether your system is able to support that procedure or not. Okay, so that's why that is one of the benefits of studying algorithm. And then, of course, when you talk about algorithm, you cannot run away from mathematics. So, hence the reason why I want you to revise back the mathematical preliminary. So, some basic mathematics formula that you need to know. Okay, because later on, in order for you to analyze your algorithm, you are going to be applying these mathematical equations. Okay, so basically, in algorithmic mathematics, you are able to describe the behavior of the program. Okay, and then as I mentioned, the reason why we want to know about algorithm so that we can analyze the performance. Okay, because in computing, performance is the currency of computing. And then the last but not least, the benefits of studying algorithm is that you can actually program the performance of your algorithm in general. Okay, so that it is not specific and it can be applied to other computing resources. So these are some of the reasons why you need to study algorithm. Okay. All right. So the properties of algorithm. Of course, you must make sure that your algorithm is correct. Your algorithm should be able to take in inputs and be able to produce the right input output. And then it must compose of a series of concrete steps. So it has to be a very deterministic step. Like what is the next step is going to happen. Okay, when you write an algorithm, and then they should not have any ambiguity. So as I mentioned, it has to be deterministic. So from one step to another, you have to know what is the next step. Okay, it cannot be something that is unknown. So algorithm must have no ambiguity, and then it must be composed of a finite number of steps. So in a sense, it will have some number of steps. So it's not something like we're going like it's not ending. So it will have some finite number of steps, as well as it must terminate. Okay, so it must have a way to actually come to an end. It must be able to terminate. All right. So these are some of the properties of algorithm. So if you look back at the definition of algorithm just now, like you're talking about it is something like used for describing how you can solve a problem. So how is it different from a computer program? Okay, so in this sense, algorithm is more like the model of a computer program. Okay, so normally in your design phase, so if you are taking software engineering, you will have if you are following the SDLC, you will have a phase where you will do design. Okay, design analysis, modeling, and so on and so forth. So normally you will do the analysis of algorithm in the design phase. Okay, so when you do and then after that, once you have the algorithm defined in the design phase, you will implement it in a computer program. Okay, so basically we can say that the computer program is actually an instance or a concrete representation of an algorithm, which is implemented in certain types of programming language. So it can be Java, it can be Python, or it can be any programming language. All right. All right. So to analyze an algorithm, okay, so there are several properties that you can analyze, okay, through algorithm. The first one is time, and then we can also analyze the space requirement, space performance, okay. So basically these are the two common ones, okay. So in terms of time, we want to see how fast it can execute, the algorithm, as well as the space performance in terms of how much memory that it will be using, and so on and so forth. And then you can also analyze the algorithm in terms of perhaps network consumption. If you're talking about the algorithm of distributed system, let's say, for example, okay, power consumption, CPU registers. So if, like, let's say you're developing some kind of maybe a real-time system, you have some constraint and you want to make sure that your algorithm is able to address those constraints. So you can also analyze algorithm in terms of those properties. Okay, so I would like to highlight for this course, we are only going to focus on time analysis. Okay, so we are not going to do any space complexity. We are just going to be looking at the running time complexity in this course. All right. But you can always read around and see what does it mean by space complexity, okay, for an algorithm. Okay, so so basically we're going to be focusing on the running time complexity of an algorithm. Here we have two examples. We have code 1 and code 2. So normally if you were given these two codes, so this is a Python code. So if you were given these two codes, which one do you think will run faster? Well, before you answer that question, if you notice, this is a Python code. Okay, so the reason why I think several session ago we were using Java for our for this course, but we switch it to Python because the syntax of Python programming is almost looks like pseudo code. Okay, it doesn't have like basically it doesn't require too much of declaration. So basically the way Python code is being written, it looks more towards a pseudocode. Okay, so that is the main reason why we changed to use Python in this course. Okay, and then it's good for you. It's a good exposure because Java, it's not that difficult for you to actually take up Python. So it is something that is good for your programming exposure as well. So yeah, so basically, so let's say for example, this is an example of two Python code. Okay, so as you can see, this code number 1. So we have sum is equals to 0, and then we have a for loop index in range 201, and then basically we are going to calculate the index, and then we're going to print the sum. Okay, and then we have code number 2 where there's some kind of mathematical formula that can actually do the same thing, which is calculate the sum of 1 until 200 until 200. Okay, so which code do you think runs faster?
Code 2.
Code 2. Why do you say code 2 is runs faster?
Because it doesn't have a loop.
It doesn't have a loop. Any other answer? Less lines?
Code
Takes one
2,
memory space?
because it only has
Code 2?
one step to go through.
Okay. Anybody else have a different answer? Yeah, so maybe less lines. And then just now, I think one of your friends said it doesn't have a loop, which is, yeah. So if you look at code 1, so basically so if you have a loop, basically you will have several number of execution, right? So you have the first call, the second call, the third call, and basically, so in a sense, it will run longer. Where in this sense, it will just execute this statement. So later on, you're going to see that there's here the running time. There will be some kind of running time here, and then this one, the running time would be equals to 1, which is constant. Okay. So yeah, so at this point, it's quite clear that we can say that code 2 runs faster because code 1 will have some loops. So you can actually see clearly that there will be several times of calling execution of statement, and code 2 we only have one statement to execute. All right. So how about the second example? So which one do you think would run faster? So in this case, we have some reverse function. So both of these are reverse function, and there's a variable, and then we have a loop here. And then for the second code, it is using some function. So which one do you think runs faster? Code 1 or code 2?
Code 2 again?
Code 2? Everybody else? Not sure? 2? Okay. So in this why you say code 2 is faster? Why do you say code 2 is faster? Class? Loop is slower maybe? Code 2 does not have a loop?
I think code 1 is faster.
You think code 1 is faster?
Yeah, because code 1 is using basic stuff, but code 2 needs to call out the function of split, then the function of reverse, then the function of join.
Yep. Okay, so in this case, for example number 2, it is not really clear. You cannot say whether code 1 it runs faster or code 2 runs faster for several reasons. Okay, so for this, maybe most of you say code 2 runs faster because there's no loop. Loop normally will run, you said may run slower. Okay, maybe you said loop is slower maybe. Okay, and code 2 there's no loop. But it depends on what happened in this function. We are not sure how does these two function happen, and maybe there is a loop actually within this function. So we are not sure whether how do you call that code 2 is actually runs faster. Okay, so even though that we have a lesson line here and there's no loop, but in order to do that, we have to also analyze what is the running time or the time taken for this function to execute. Okay, so it doesn't necessarily mean that the lines of code will say that an algorithm may run faster. So it depends on how the execution is being done. Okay, faster to type. Yeah, I'm a very slow typer, so I prefer talking straight away. It's much faster. Okay, all right. So we have seen those two examples just now. So what do you think the notation that we can use to describe the running time of the algorithm in the previous slide? How would you like say or describe the running time for those algorithms that we have seen in the previous slide?
Big O notation.
I guess one of your friends is already going through the slide and he knows what is the notation. Yeah, we can use the big O notation, which is the asymptotic notation, all right, in order to describe the running time complexity. But that is if we know that we can use the notation. That is a very specific notation for us to do asymptotic analysis on how on what is the running time complexity of a program. But normally, what you would do is probably you will run it in some machine and observe the execution time, right? So sometimes so basically I think in Java or is it in Python you use the time statement, and then you will see what is the execution time for those code. And by you doing that, you probably will observe that sometimes one code perform better based on certain input, okay, and perhaps on a different machine it will perform differently as well. So if we describe the performance of a program using this one, so there's some dependency in terms of the type of input, the type of implementation, the type of machine that you apply it to. So in a sense, we need a way to have to be able to describe an algorithm's performance in a more generic terms. Okay, so that is why we are using this asymptotic notation for doing the asymptotic analysis. Okay. All right. So basically, you can use the asymptotic analysis to calculate what is the running time complexity or the space complexity of an algorithm in terms of the input size. Okay. All right. Okay. So far, so good. Yeah. Any question? Good. All right. So let's continue to look at the running time complexity and how we can use the asymptotic analysis. Okay. So before we go further, let's look at the time function characteristic. Okay, so when we look at algorithm, okay, we are actually looking at the how do you call that, the performance in terms of the time function. Okay, so in a program or in an algorithm, you can have either constant, okay, logarithmic, linear, quadratic, cubic, and exponential. Okay, so these are some of the function that you may have to describe what is the characteristic of your algorithm. Okay, so here as you can see, okay, so these are the graphs. So if like let's say you have several algorithm with different time function. Okay, so if like let's say we have this function which is n to the power of 2. So if like let's say you have this would be so this would be the time, okay, and then this would be the number of inputs, okay, which is n. All right. So as you can see, if you plot what is the running time for that algorithm in terms of the inputs, you will get if like let's say the time function for the algorithm is quadratic, your graph is going to look like this. Okay, when you plot according to the number of inputs in relates to the execution time. Okay. And then if like let's say your time function for the algorithm is n log n, this would be the graph, and so on and so forth. So basically linear is like this. So if like let's say you have a linear function, so this is how your graph is going to look like. N log to n, you're going to get something like this. Okay, so these are some of the time function graph looks like. Okay, so if you look here, I have given you like a list of how do you call that, comparison on which one is smaller, which time function is smaller than which. Okay, so basically the smallest would be constant. Okay, the running time is constant, which is equals to 1. And then if like you have the time function log n, that time function will always be bigger than the constant. And then this one is square root n, okay, is bigger than log n, and so on and so forth. Here we have linear, which is smaller than, we will have smaller time function n log n, and squared, and cubed, and so on and so forth. And then we have the exponential in the end. Okay, so this is the sequence. Okay, so please remember this sequence, because in order for you to make a comparison between the running time complexity of several functions, this will help you determine whether it is going to be upper bound or lower bound that function. Okay. All right. So basically, this graph is called the growth of function. Okay. So it is actually when you are doing the analysis, you are actually looking at what is the rate of growth or order of growth for an algorithm. Okay, the running time of the algorithm. So so basically, the rate of growth is how we are going to observe how is the running time increases as a function as opposed to the number of input that we're going to have. Okay, and normally we represent it as Tn. Okay, so you can have something like that. So if, like, let's say you have an algorithm which is fn is equals to n squared, let's say, for example. So basically we can represent what is the running time complexity as Tn is equals to order of n squared, let's say, for example. So this is how you're going to write your running time complexity. All right. So we're going to look at this simple example. So let's say we have these two functions. The first one is n squared, which is represented in this red line. And then we have the n cube, which is represented in green. So which one would you say have the higher growth rate in this case?
Green.
The green one. Okay, so this one, if you look at this one as well, so we have one function is n squared, right? So we have one function is n squared, and n cube. So we know that the n cube will have a higher growth rate. All right. So basically, the green one will have a higher growth rate. Okay. So in that sense, which algorithm is better? Those who have a higher growth rate or a lower growth rate? Which one is better?
Low.
Lower? Yeah. So we always want to have our growth rate to be very low, and the best one, if we can get our algorithm time function to be constant, right? Basically towards Tn, sorry. So basically, the best running time complexity is that we want to have our running time complexity towards constant, okay, order of 1, okay, which is constant. Okay. All right. So I also want to highlight to you about this n naught. Okay. So if you notice that for this graph, there are some region, okay, so this region, where if you consider the n before the n naught, you will see that the growth rate is actually of n cube is lower than the n n squared. Okay, so for doing an algorithm analysis, we always consider the value of n that is after the intersection of the two graph. Okay, and this intersection normally we will call it the n node. Okay, so we will do the analysis for n that is bigger than the n node. Okay, all right. So just now your friend mentioned about the big O notation. Okay, so for the asymptotic notation, big O is one of the three main asymptotic notation. So under the asymptotic notation, we have the big O notation, we have the big omega. Okay, we have the big O, and then we have the big omega and the big theta notation. Okay, so the big O we represent it with a capital O. Okay, big omega we have this, I don't know, is it ohm? We call it the ohm symbol. Yeah, so we have that symbol for big omega. Big theta is like this notation, and each of them, so for big O normally it will represent the upper bound. All right, big omega will represent the lower bound, and then normally big theta will represent the average time. Okay, but actually it's not really directly talking about the worst time, the best time. I'm going to be talking to you, I'm going to be showing you further what does it mean by the worst time or the best time. So the asymptotic notation is more used to describe the boundary, okay, the upper bound and the lower bound. And the worst time and the best time, sometimes it is not directly related to the big O or the big omega and the big theta. So later I'm going to show you what do I mean by this. Okay, so for now, just take a note that big O is for upper bound, omega is for the lower bound, and the theta is for the average. Okay, so where it is the upper bound and also lower bounding the function. So let's look at, before that, in asymptotic notation, okay, so if let's say we have this time function, fn, n cubed plus n plus 5. So the asymptotic notation, okay, for asymptotic notation, we only consider the higher order term. Okay, in this case, it is the n cubed. So when we write the running time complexity for this function, it will be Tn big O or big theta of n to the power of 3. Okay, so we don't really look into what is the constant coefficient as well as the lower order term. All right, so the reason why we don't really look at the coefficient as well as the lower order term is, I'm not going to go through this like very specifically, but if you replace the value of the n, you will see that it is not going to affect much in terms of what is the running time. Okay, so if like, let's say for example, maybe if you have let's say your n is 10, if you really put in the 10 into this equation, this is the value you get. And if you only consider the higher order term, you're going to get this. So it's not that much different, okay, whether you are considering the lower order term and the coefficient or not. Okay, so that is the reason why we don't really, we only look for the higher order term in terms of the running time complexity. Okay, so this is another example of why we don't really consider the lower order term. Okay, so this is the how do you call that, the definition for big O, big omega, and big theta. So for the big O, we can say that Gn is upper bounding Fn, and we can write this. Okay, Fn is equals to big O of Gn. So basically, your graph, if like, let's say we have this graph, so we're gonna have like maybe this is f of n. Okay, the graph. We're gonna have Gn upper bounding the Fn. Okay, so this would be this represent this. Okay, and if you can see the formal definition for big O is we have f of n is smaller than equals to some constant of uh, times the gn. Okay, so c or k, so they are the same, so coefficient, so in this case it's represented by k. You can also represent it by c. Okay, and k is a positive number. All right, so this is the formal definition for big O. And then we have the big omega. So in this case, the big omega, so if like let's say we have a graph for fn, and we say the fn is lower bound by gn, you're going to have the gn lower bounding the fn. Okay, and in this case the formal definition would be fn is bigger or equals to some c of g of n. Okay, and then for the big theta, so like let's say you have a graph and you have some function fn. You also have some function above. So in this case, they call it, this is case, so I'm just going to use C1. C1 dot fn, which is upper bounding the fn function. And you also have the lower one with another coefficient, which is, sorry, this is actually gn. G of n. Okay, so gn function can be an upper bound or lower bound of function fn. Okay, where as you can see here, this is the formal definition. So you have gn, some c1 of g of n smaller than function fn, and who is also smaller than some c2 of g of n. Okay, so this is the formal definition of big O notation. Sorry, asymptotic notation. Big O, big omega, and big theta. Okay, so do you need a rest? Are you good so far? Class?
Small.
Sorry?
Wait, so
A small rest.
Okay, so we're gonna rest for a while.
so big theta will always have like two graphs. We always have like two possible lines graph. Yeah.
Big theta is like when you have a big theta, it is saying that that function can be an upper bound for that function, or can be the lower bound of that function. But that happens depends on the value of the c. If the c value changes, the graph can either go up or it can go lower than the fn. I'm going to show you an example later.
Okay.
Okay, so let's take like a quick break. 5-minute break. Okay, 5 minutes. Someone requested 5 minutes. Okay. In the meantime, if you have any question in regards to the what is expected from this module, or if you have any question, you can talk to me. All right. So at the moment we are 59. So 3 or 5. Have you signed your attendance, class? So I have 96. Okay. For those of you, we are definitely going to have a lot of group work. I noticed that for group tutorial 1 and tutorial 2, 2, we are combining the two groups. So I don't know how, because normally during the tutorial is when I get to talk to my students. But then when they combine the tutorial time between the two groups, I need to find another strategy to make sure that I can reach out to you all. Okay, because I don't really like to have a big group during tutorial, because it's very difficult for me to talk to you, and then it's very difficult for you to talk to me. It's just like during lecture. I don't know, would you prefer something like activity during the tutorial rather than, like answering the tutorial question? So I was thinking about doing some kind of active learning method during the tutorial and labs. We have 2 hours, right, for our tutorial and lab. But if you want to do that, you probably need to do some preparation a little bit, because we cannot for some of the topic I probably need to give you some instruction for preparation before you go for the class. But I'm still trying to figure out how am I going to handle the tutorial 1 and tutorial 2, because I have 35 in tutorial 1. Tutorial 2 I have 35 as well, but if there's if there's no problem, then I probably will change tutorial 2 with tutorial 4. Because the Iterative class is very few. There's only like 5-10 students inside there. Or maybe perhaps you can go into the Iterative class, you know.
But the time will still be the same, right?
It's still the same. It will still be the same. Yeah. So for tutorial 1, tutorial 2, the time is the same. So it's going to be a big group. I don't know whether like I can combine all 3 groups in one session. But I really like prefer to have a smaller group during tutorial and during lab. Then again, it will be like, so like some of you will be somewhere at the back there. So at least that is when I will have a smaller group and I can focus more on the student, and I can talk more. I mean, like everybody can join in. So I think another way to actually do this is to try and do active learning, different method rather than just answering question. So I need to figure out how should we go about doing this. Maybe we need to do some breakout team or something like that. So please, for me, I don't have any requirements on how you want to form your teams. So your group member. So maybe you can look around for group members, like 5 to 6 people, so that we can straight away, like do group activities during our lab and tutorial. All right. So, okay. All right. Actually, for the Telegram, right? I noticed that you also will have to join like a discussion group, if I'm not mistaken, because the one that I gave is a channel. So, you probably need to join how do you call that? The discussion group or something. I don't remember what's it called. So I think once I post something, and then when you start replying to that post, you will be sent to another chat group. So I don't know how to generate that. So maybe once we have that generated, I will also give you the link to that chat. Because from the previous session, some of my students don't know that we have that chat. So they missed out a lot of conversation in there. Okay. All right. So let's continue. Let's look at the big O notation. Okay. So if you remember just now, big O is actually referring to a function that is upper bounding another function. And we have the formal definition as Fn is equals to big O of Gn. So as you can see, the Gn is upper bounding this function. Okay, and then we have some coefficient here. All right. And for the big omega notation, okay, we can say that Fn is equals to big omega of Gn, whereby the function of Gn with some coefficient is lower bounding the function Fn. All right. So this is the definition of big O and big omega. Okay, so if you notice here, we are considering the end node here. Okay. So basically, when you when you look at the running time complexity or whether the function is upper bounding or lower bounding, we always look after the n that is after the end node. Okay. So let's look at one example. Okay, so this is quite obvious. Okay, so we have we have Fn n squared and Gn is n cubed. So if we plot this on a graph, it will look something like this. And it is obvious that we can say that this Fn function is equals to BO of G of n. Okay. So if you look back at the series here, so so Fn is n cubed. So this is n squared. Okay, so you can actually say that whatever function that you have here is actually the upper bound is upper bounding n squared. Okay, upper bounding. Okay, and whatever function that is below here, it would be lower bounding the n squared. And then basically here, basically the average. Okay, you can find what is the average. So or the big theta. All right. So basically, these are some of the things that you can actually use to see whether it is a big O or big omega or big theta. Okay. In this case, the C for this is actually 1. Okay. So if let's say we have a different value of C, or in this or in this case we use K. So if let's say we have the value of C which is less than 0, still positive but less than 0, and you will see here that the function goes below the n squared. Okay, so the function goes below the n squared, and from the definition we know that in order for Fn to be BO of Gn, you need to have Fn is smaller than some coefficient, some constant Gn. But if we have this value and we put in the value in, and then let's say for example we said n is equals to 1, let's say for example, and we get this graph. We actually prove, so basically this one is 1 is smaller than equals to 0.031 and so on and so forth. So basically this is not right. right? So what happened here? When we know supposedly whatever that is bigger than n squared should be big O. What happened here? Anybody knows?
The coefficient is smaller than 1.
No, it's still positive. It still fulfill it still fulfill the how do you call that, the coefficient requirement. It's still positive.
Hmm.
Anybody knows? Because we know that whatever time function that is bigger than n cube is definitely supposed to be bigger than n squared. But in this case, when we put in a number of constant, in this case positive number 0.03, and the graph goes goes below. Do you know what happened?
Initially, the graph of n cube might be smaller than the graph of n square, but eventually, as the n increase, the graph will of n cube will how to say overtake the graph of n square.
Okay, so thank you, John. Yes, that's right. Because if we zoom out, so basically if we increase, remember the n node? This n, if like, let's say at this point, we take n is equals to 8. 8 is actually lesser than n node. Okay, so if we zoom out, at some point of time, at some point of the graph, okay, where the graph intersect again, the n node, okay, you will always get the n cube bigger than the n squared. Okay, so that is the reason why. Okay, so you have to make sure that when you do the analysis, your n, the value of your n is bigger than this n naught. Okay, so you have to make sure that you find what is the intersection point, and you when you want to do the analysis, use the n that is after, that is bigger than your n naught. Okay, so yeah, so in this case, we still can see that the Fn is the big O of G of n. All right. Okay. All right. So that is for the big O. Same goes for the big omegas. So it's supposed to be it's the other way around. So the concept is the same. I'm not gonna be doing that here, but I believe that you can actually apply. The concept is still the same, but it is lower bounding the function. All right. So in this case, you can also do some formal justification. So in a sense, how we can prove that function, that definition is true. Okay. So in this case, what we are doing is to find what is the value of C and what is the value of N, that we can prove there exists some value of C and some value of N that will prove this definition is true. Okay, so in this case, let's see one example where we want to prove that that Fn is BO of Gn. So if like, let's say we have our Fn, so let's say we have our Fn is 3n plus 2 and our Gn is n squared. Okay, and we want to see, we want to check whether Fn is BO of Gn. So according to this, is this statement true? Is Fn is BO of Gn is equals to BO of Gn? Class? Yes or no? class?
No.
It's not?
Fn is.
It's yes, right? Because Gn, here our Gn is n squared, our Fn is, this one is linear, Fn is n. So if we look at this list, our n is here, our n squared is here. So definitely n squared is the big O of big O of Fn, right? So we know that this is true. So how do we prove that this statement is true? Is we need to find some value of C and one value of C or one value and one value of N where we can prove this statement is correct. So in this case, okay, so in this case, if we want to prove that Fn is the big O of Gn, the formal definition is this one, right? So we have this formal definition. So we put in our Fn smaller than equals to some coefficient times n squared. Okay. So let's say, for example, so we know that this is 3 and we want to make sure that this value is bigger than this one. So we can say that we can just, like from this, we can assume that if, let's say, we take n is more equals or bigger than 4, and the value of C is equals to 1, we can actually prove that this statement is correct. Okay, so because if we put in the value in right, if we put the value in, we can actually prove this statement is correct. Okay. Let's say, for example, we put 3 times 4, 12 plus 2 is smaller than equals to 1 times 4 squared. So we get 3 times 4 is 12, 14 is smaller than 16. Therefore, we have proven that this is true. Okay. So all we have to do is just find some value that can prove this statement Gn is upper bounding the Fn. Okay. So the value of this can vary. You can have a different value of C. We can have a different value of N. But we always try to look what is the smallest value of C and the smallest value of N that we can put into the equation that we can prove whether the statement is true. Okay. And that is the first example on how you can prove the statement. This is for the big omega, same thing. We have to find what is the value of C, what is the value of N, where we can find some that we can actually prove that this statement is true. Okay, Gn is bigger than some coefficient Fn. And if, like, let's say we put our C is equals to 1 and N is N is equals to 4 or any number bigger than 4 into this equation, we can actually prove that N squared is bigger than 3N plus 2. 3N plus 2. Okay? Is that okay? Are you guys getting this? Maybe later on you can try and see whether you can do this. Okay.
I actually have a question.
Yeah.
The previous example, if I used the 0.5 as my C, the n squared would be smaller than the 3n plus 2.
Yeah.
So wouldn't that mean that it's lower
False?
bounding it? Yeah.
Meaning that your n value is
Less than 1.
yeah, it's either less than 1 or it's not the n, it's not bigger than the n naught. So if your
Oh.
C is smaller, your N must be bigger.
Oh, okay.
Yeah, because whatever it is, when you plot it, that graph at one point after the N naught, it will go up.
Mm.
If we follow the rule, the sequence. Okay?
Okay.
Is that right?
Yeah.
Okay. All right. So for the big theta notation, so if you look at the previous definition, the function is both upper bounding and lower bounding the fn. Okay. So for example, let's say we have this, we can see that this fn, okay, this fn is upper bounded by this gn function with some coefficient value, and the same function gn can also be a lower bounding fn with another coefficient value. Okay, so in this case we would say that this fn is the big theta of gn. Okay, so how do we prove this? Oh, so let's just look at one example. Okay, so in this case, we have, let's say, for example, we have n squared, fn is n squared, and gn is n squared plus n plus 100. Okay, so if we plot this, okay, if we plot this is the graph that we're going to get, right? So we're going to get this gn, and this is your fn. So therefore, it is so we, in this case, we say our fn is the big O of gn. Okay, and then in this sense, if we want to look at the definition, we use the formal definition again. Fn is smaller and equals to some constant. So in this case, we is C2, I guess, if it is looking at according to this. So we call it C2 of g of n. So in this case, this C2 is 1, right? So this is represented by this graph. Okay. So therefore, we can say that for some value of Cn, Gn is upper bounding the Fn. All right. So if like let's say we change so if like let's say we increase the C, we can see that it is still upper bounding the Fn. So this is Fn. So if like let's say we have another value of C, we still have the Gn upper bounding the Fn. But then if we have, let's say, for example, another positive value, so let's say we have 0.86 something, we can see that the graph goes below Fn. This Gn goes below Fn. So we have our Fn, and now our Gn is below. And this one, we can say that this would be our C1 value. Okay, so the C1 is equals to, when we have a C1 equals to 0.860708, the graph is lower bounding this Fn. So therefore, we can say that Fn is equals to the big theta of G of n. Okay, do you get what I mean?
So that big theta would usually have the Fn, the equation of Fn and Gn in big theta would usually mostly be similar.
Yeah, normally the function would be similar, because if you remember when I showed you the upper bounding, I remember, 1 second, the thing where, so normally if you have two equation that have the same time function, normally you can consider it as a big theta, right? Okay. All right, so the formal justification is the same. So in this case, we are supposed to have, so just now is C1 is lower, right? So C1 of G C1 of G of n is lower than equals to Fn, which is lower than C2 G of n. Okay, so this would be the formal definition. So in order for us to prove this, we need to find some value, one value of C, one value of C1, one value of C2, and one value of n that can prove this statement is correct. Okay, this is true. Okay, so you can look at this later. All right, because I think we still have got a number of slides that I need to fly through. Okay, so I hope so far you are following me. Yeah, I know it's quite heavy for the first day. But it is this concept. This is the basic concept. I think in the next class, once you get the idea of what algorithm is about and the running time complexity, then it will be much easier for you to understand the following lecture. So the first lecture is very, very important. You need to understand this before you can actually go to the next, easily understand what the next lecture is going to be talking about, because you're going to talk a lot about the running time complexity. If you don't know how to use the asymptotic notation, then you're going to have a problem. Okay, so please make sure that you get this before next class. All right. All right. So when I talk about the asymptotic notation, I also mentioned about best, average, and worst case running time. Okay, so normally when we do the analysis, we always want to look into what is the worst running time for that algorithm. Okay, so normally the average time is almost towards the worst case running time, except for I think one of the algorithm that we're going to be looking at the analysis, and you will see quite an interesting property where you will see the best case, the worst case, and how is the running time complexity for the algorithm. But we're going to be looking at that later. Okay, and for the best time, normally we don't really consider, because it is very not very rare, but it's pretty uncommon that your algorithm is going to run at best time unless you are lucky. Okay, so but then we have these three types of cases, running time case. Okay, we have the best, average, and the worst case. So in the for the algorithm analysis, the running time analysis of algorithm, we always interested in the worst case running time. Okay, so basically what is the worst case running time that you can have for the algorithm? So maybe I can explain this to you using this very simple example first. Okay, so like let's say we have this linear search. So linear search, basically if you have so basically if we have a key to be searched, and you need to search for the key in the array. Okay, so like let's say for example the key is 50, and you do a search, so you compare with array 0, array 1, and then you will find the key in array number 2. Okay, so that is what do you mean by linear search. So in this case, the algorithm for linear search, so the best case is how would you describe the best case for linear search? Anybody? What is the best case? Class?
And
What is the best case?
It's one.
Sorted? Not really, because we are not really looking whether we want to find the smallest or the biggest. So I believe that sorted doesn't really how do you call that related to it. I think Daniel said the best would be constant, right? Order of 1. Okay, how do you get order of 1? Daniel? How do you get order of 1? Big O of 1. Big O1. Yes, the element that we want to find is the first element. So if like, let's say every time the key that you want to look that you're looking for in the array happens to be in array 0. Therefore, there's no additional comparison. The running time complexity for the best case would be constant, which is order of 1 or big O of 1. So, okay, please take note. Sometimes I use order of 1. I am referring to the big O of 1. Okay. So, yeah, so it will be constant. Okay, how about the worst? What is the worst case?
It will be at the final index value.
Yeah, which is
In this
you
case,
have
9.
to have, yeah, which is 9. So which is, so normally the number, it would be the number of element. So normally the number of element we represent it in n. So basically the running time complexity for the worst case running time complexity for linear search should be order of n, right? So how about the average running time for this one?
Average should be O n over 2. That
N over 2? Yeah, so basically it would be not really n over 2, because in order for us to be able to find what is the average, we need to find what is the all possible cases over number of cases. Okay, so in this case, the number of comparison that you might do might be one time, or you might have to do 2 comparison. Maybe the key is in the second position, or maybe it is in the third position where you will do 3 times, 3 comparison, or maybe you will do 4 comparison, right? Up until n comparison, right? Over n, right? So that would be the average case. So in this case, we know that this is arithmetic series, right? So, sorry, so I need to go to this one. So we know that this can be represented as n plus 1 over n, and therefore we get n. So this one, so we get
n plus 1 by n.
n plus 1 by n, right? Which is the final one would be order of n. So this one is n, so n plus 1 over n, right? And therefore, because we only need to get what is the higher order term in this case, and therefore we get order of n. So yeah, so basically the average case for the linear search should be order of n. So as I mentioned, normally the average case would be more towards the worst case. So it's proven here. So in a sense, for the average case for linear search should be order of n. Do you get what I mean here? Yeah. Okay, so this is what I mean by best case, average case, and worst case running time. Okay, so I would also like to highlight a little bit about this, because when you talk about the worst case, the best case, you know, your best case can also be written as one, which is constant. Okay, so your Tn for best case, you can also write it as 1. You can also write it as the big O of 1. You can also write it as the big omega of 1, or the big theta of 1. Okay, so you may find that when you when you read some notes, you may find that sometimes they use the big theta or the big O. Okay, so when you're talking about the worst case running time, the best case running time, the average running time, The asymptotic notation does not really indicate whether it is the best time or the worst case or the average case. Okay, so when you read later on, you may find that some people will use the big theta notation and some will use the big O notation. So they are referring to the same thing. All right. Sorry. So comma for average, can it be order of 1 because and plus 1 can be 1 approximately? No, we have to look at the term for that. N plus 1 over n. The highest order term is n. So the average, yeah, it can go to 1 because the average can go but normally when we calculate it, the average normally it is all already towards the worst case running time. Okay. All right. So until now, you should be able to know how to use the asymptotic notation and to do like a very simple asymptotic analysis. So we are going to, I guess for the representing algorithm is quite simple. So normally we will use pseudocode. And as I mentioned, the reason why we choose to change to Python is because the syntax for Python almost look like pseudocode. Okay. So, but it is not necessarily mean that an algorithm need to be represented using Python-like syntax. It can be any syntax that can be understood by whoever that is supposed to read the algorithm. Okay, so as long but generically algorithm should be implementation independent. So it is not referring to certain implementation, but you can actually adopt like programming syntax for describing an algorithm. Okay, so like let's say for example, if you have the for loop, like maybe I is equal 0, I less than n, I plus plus, or maybe you can use if like let's say for example well, maybe I will give you like a simple function. So if like let's say I have a swap a b, maybe you can have something like temporary is equals to a is equals to b, and b is equals to temporary. It can be something like this, your pseudocode, okay? Or maybe you can have something like maybe swap A, B, and then maybe you will do something like begin, and then we have temp equals A, and so on and so forth. So the pseudocode, you can use any representation as long as it is not really specific to as long as it is understandable. Okay, so you can adopt some programming syntax when you write your pseudocode. But basically, bottom line, when you write algorithm, there's no specific way to write an algorithm. There's no specific way to write a pseudocode, as long as it is understandable. Okay, and it has to be, and it is definitely language programming language independent. So it's not specific. Okay, it's very generic language. Okay, so these are some convention that you can apply when you write pseudocode. Again, I'm not going to be focusing much on this. As long as you write pseudocode and it is understandable, then it is accepted. Okay, so in our course, we're going to be looking at two types of algorithm. We're going to be looking at the iterative algorithm as well as the recursive. So to analyze these two type of algorithm is different. Okay, even though that you can have a program or an algorithm that is iterative and you can convert it into recursive, but the way you do the analysis of the two types of algorithm is different. Okay, so we will try to look at the first type first, which is the iterative algorithm, and how we can analyze the iterative algorithm. So here, we have some example of an iterative algorithm. Okay, so I'm sure you are familiar with this. Even though this is Python, I'm sure you can still make sense of the syntax. So in this sense, in Python, in order for you to do the for loop, you have to say for I in some range. So this is 0 to 10 and increment by 1, you print hello. Or this is the while loop where you have I is equals to 1. While I is less than 10, you do the I plus 1. Okay, so these are example of some iterative code. All right. So how are we going to calculate what is the running time complexity for iterative algorithm? Okay, so for the analysis of iterative algorithm, we need to determine what is the higher order term by calculating how many times a statement is executed. Okay, we need to calculate how many times an operation is being done, how many times we do the comparison, how many loops do you have, pointer reference, as well as the function call. So we need to calculate individually how many times each of these statement is being executed. Okay, so for iterative algorithm, it's pretty straightforward. We just calculate how many times each of the statement is being executed. Okay, so as I mentioned just now, you can have an iterative program and represent your solution in an iterative algorithm, and you can also have a similar representation using recursion. It's just that when you want to do the running time complexity analysis, the method is different. So for the iterative, you can count what is the how many times you execute the statement. Okay, and for the recursion, we're going to look at it in the next lecture. All right, so I have like this one example of insertion sort. Do you know what is insertion sort? Do you know what is insertion sort? Class? Have you come across insertion sort?
A type of sorting system, like bubble sort, but like, well, yeah, a type of sorting system.
Yeah, it is a sorting system. We're going to be looking at more ways to sort in our sorting topic. So all of you only know how to use bubble sort. Yeah? Only bubble sort? For programming?
In data structures, we actually learn until quick sort, if I'm not mistaken.
Quick sort. That is my favorite one. I'm sure you're gonna have fun when we do the analysis of quick sort. Okay, that's nice. So you have some background of other sorting, other types of sorting other than bubble sort. So insertion sort is one sorting algorithm. Okay, whereby you do some comparison. It's like something like you have a deck of cards and you try to compare and then you insert it in between. So if let's say you try to arrange a deck of cards, you compare and then you insert it. Basically that is the concept. Okay, so this is the pseudocode for insertion sort. Okay, so if you notice, this pseudocode does not really this is from Common. So Common book use this convention for their pseudocode. You may find other ways to write pseudocode, but this is one of the way that you can write your algorithm, your pseudocode. Okay, so as you can see here, we have loop. Okay, and then we have a statement where you insert A into the sorted sequence. You also have a while loop here and some comparing comparing statement here. and some assignment code here. And yeah, and finally you will like basically you do the comparison. If it is smaller or bigger, you will somehow slot it into place. Okay, so basically these are what this algorithm is about. Okay, so in order for us to analyze the insertion sort, all right, we can apply the asymptotic analysis onto the algorithm. All right, so intuitively we can say that the running time complexity, of course, will depend on the input, right? So I believe one of your friend did say something about the sorted list when we do the linear search just now. So in this sense, when you want to sort an array, the best running time complexity can be achieved if the input array that we get is already sorted. Okay, so of course sorted sequence will give you the best running time. Okay, so but then as I mentioned, when we do the analysis, we always want to look for what are the worst case running time complexity of it. Okay, so so basically we need to have the to parameterize the running time by the size of input, because shorter sequence will be easier to sort than long ones, and so on and so forth. Okay, so in this case, for the input values, the n values, we are not going to make any assumption, but we are going to always assume that n is not always small. Okay, so it's not 1 or 2, it will be like more than that. All right, so that is our assumption. Okay, so as I mentioned just now, for an iterative program, how we're going to calculate the cost is we're going to calculate for each of the statement how many times it execute. Okay, so basically for insertion sort, for each of the statement, these are the number of time it is being executed. Okay, for now, I am not going to like really go into each of these statements, but I'm just going to show you the overall on how you can actually calculate what is the running time complexity for insertion sort. Okay, so I think I'm going to give you a simpler example later on. So for the running time complexity for this one, so this one is the best case. This is the running time complexity for insertion sort. So it is the sum of all the costs for executing each of the statement in the insertion sort algorithm. All right. So for the best running time for insertion sort, okay. So in this sense, when we go into this loop, we need to find what is the best time, okay, for that statement to execute. So in this case, we know that it is all n minus 1, so it's not going to be more than that. So once we sort of like put what is the expected best running time for that insertion sort, we can see that the highest order term in this running time complexity is linear. Okay, so therefore we can say that the best case running time for insertion sort is order of n. Okay, and for the worst case, so notice that for C5, we consider what is the worst case that can happen in that statement. We expand it, the running time complexity, and then the highest order term for this running time complexity is quadratic. Okay, so this one you will get the n squared. So therefore, the worst case running time for insertion sort is order of n squared. Okay, so I know you're going to be like, what's going on here? I'm not going to be, maybe later on you can look back at it. I'm going to give you a simpler example. Okay, maybe I'll just go straight away into this one, example number 1. So if like, let's say we have a simpler iterative program, okay, whereby in this case, we call it as function 1, and we have a simple for loop, okay, where this for loop is running from 1 up until n, and it is increasing by 1. So now we need to find out how many times this print statement is going to happen. Okay, so in this case, how many times that this print statement is gonna happen?
N times.
It will be up until n times. So if let's say n is equals to 5, meaning we're gonna have n, we're gonna have 5 hello world statement printed. Okay, meaning it's going to be executing 5 times. Okay, so 5 times. So therefore, we can say the Tn for this function one is equals to order of n. Okay, so this is the simpler version. It's the same as the one the insertion sort, but then because insertion sort have comparison, and then there's a swapping occurring, so therefore you need to take into consideration how many times those comparison is being done, those operation is being done within the insertion sort. Okay, so this is the simplest one. Let's look at another example. Okay, so for example, here we have another function 2, but now we have two loops. Okay, so we have the first loop here, and then we have a nested loop here. So now we need to find out how many times that this statement is going to be executed. Okay, so how do we do this? We look at how many times that this for loop is going to occur, because this for loop will determine how many times the inside for loop is going to happen, right? So in this case, what is how many times that the first for loop is going to execute? It will execute n times.
N
Yeah.
times.
Yep. So for the nested loop, okay, it will be n times. How many
N.
times for the nested loop will happen?
It will be n squared.
It would be another n time. For this loop, it's going to be another n time. So therefore, what it means that for this nested loop, it will be this n times another n. Okay. For this hello world is being printed. So therefore, we can say that the running time complexity for this one would be order of n squared, right? All right. So for the third example, do you know how do I already have answered there. I should have not put the answer there and let you do it. But do you know how do I get for loop number 1 is n over 2 times, loop 2 n over 2 times, and loop 3 log n base 2? Class? It's already 4:53. I know it's quite heavy for the first day, but hopefully maybe we're just going to look at this last one and try to finish it within 5 minutes. Do you know how do you get the n over 2 times?
Because it starts off with half of n, so the increment, the total increment will just be half of the value of n.
Okay, yes. So if you can see here, the starting value of n is half n over 2, which will run up until n. So therefore, we can say that the loop will happen in n over 2 times. Same goes for the inner loop. Okay, so for this loop is n over 2 times. So but for the third nested loop, do you know how do we get the log n base 2?
Because the increment is a constant to the power of 2.
Okay, so do you know how do we get the log n base 2? We try to trace what is the value. Okay, so in this sense, So so in this sense, we try to track what is the value of k. Okay, how does the k increase? So let's find out. Okay, so so in this sense we have k, and k is equals to 1. So when k is 1, k squared would be 1, right? Sorry, k times 2 would be 1. So when k is 2, k times 2 would be 4. If 3, it would be
6.
6, right? This one we can actually say this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and then 4 would be 4
1
times.
is power.
Sorry.
1 is 2 power 0.
Sorry, 2 power 0. 1, 2 times 2 is 4. Wait 1 second. How to oh yeah, okay. 2 to the power of 4, 0. 1, 1, so 2 to the power of 0 is 1. 2 to the power of...
Doctor,
Are you sure?
the K1 should equals to 2. 1 times 2 should be 2.
2. Sorry. Okay. I think I'm already like what? Okay, so 1 times 2 will be 2. No wonder. Okay, so this is 2 to the power of 1. No wonder. So this is so k times 2. So 4. So this is 2 to the power of 2. 3. So 3 times 2 will be 6. So sorry, 3 times 2, 3 times 6 is 9. Oh my god. Right?
3
Yes.
times 2.
6 only,
Sorry,
ma'am.
3 times 2 is 6. So it's not, it's 4, it's 4. It is actually 4 times 2. So currently the k is 4. So 4 times 2 is 8. So this is 2 to the power of 3. So 8 times 2, it would be 16, right? 16.
Yes.
So 2 to the power of 4, right? So basically, in order for us to know, k will stop, all right, when k is bigger than n, right? So basically, this will occur some k times. So this k will go up until some k value, right? Some k times. So basically here we can assume that this is what we call times. I'm going to if you don't if you missed out, if you don't understand this one, we're going to repeat this later on. So so basically this is the time. So we can say that it will stop at k 2 to the power of k. And we know that k it stops when k is bigger than n, right? So we know that the k is 2 to the power of k must be bigger than or equals to n, and therefore how many times? It is actually log n base 2. Do you know how to change into log this one?
Yes.
Yeah?
Yes.
Yeah, so that is how you get the log n base 2. So therefore, the total running time complexity for this one would be n over 2 times n over 2 times log n base 2. And therefore, you get this n squared log n base 2. Okay, so again, we omit the coefficient. We only take the higher order term for our running time complexity. So therefore, the running time complexity is order of n squared log n base 2. Are you alright? It's already 5 o'clock. Maybe I will repeat this. Yeah.
So
So
if it's
yeah.
iterative, then you add. If it's recursive, you multiply.
Not really.
Not really. Okay, well, wrong.
No.
Never mind.
So we're gonna see next week. We're gonna see the recursive. How we can do analysis on a recursive program, a recursive algorithm. We have 3 methods to actually do it. So yeah, so we're gonna be looking into further into the recursive function. Okay. All right. So we are going to proceed with normal tutorials. So maybe for those, I think I have included some practice question below. Okay, try to do it, and then perhaps during the tutorial we can discuss it. I think I also have like a tutorial question on spectrum. So maybe you can try that one out, and then later on maybe we can have a discussion if you cannot do it for the iterative function. Is that all right? Okay.
Okay.
All right.
Yes.
I hope you're not overwhelmed for your first class.
Just a bit.
Yeah. But so far so good, right? Is it okay? Do you think that this is quite hard?
It's not
Yeah.
easy.
It's
I think it's manageable. Hopefully.
yeah. Good. It's good to hear. It's good that you don't feel too overwhelmed, that you feel like, oh my god, what is going on? Okay, so again, please make sure that whatever concept, the BO notation, how do you call that, the asymptotic analysis, make sure you get it properly, because else, once we go through the next lecture, like when we start talking about the running time complexity, the analysis, how we're going to calculate the running time complexity, if you don't understand what does it mean by the best case, the worst case, upper bound, lower bound, then you probably cannot make sense of how we do the algorithm analysis. Okay, good. Okay.
Actually,
Yeah.
just one question. I mean, this refers to the big omega and big O, I think, the upper bound, lower bound.
Yeah.
Does it matter? Can the upper bound and lower bound be any value? Like, say, the Fn is n squared. Can the upper bound be just like n power, like the value given is n power 5? Can that be an upper bound, or is it like depending on how there's other factors?
Okay, so what is the polynomial equation again for the upper bound? N to the power of 5.
Yeah, for example, n power 5, yes.
That would definitely be upper bound of n squared.
So anything above, anything like on the scale that's on the, I guess, on the right side will definitely be considered as an upper bound, regardless of whatever the value is. Okay.
Yeah.
Okay.
Because whatever it is after the n naught, if you plot the graph based on the time function, the time function for that algorithm, if you plot the graph at one point, it will definitely beat the n squared.
Okay. Yeah.
After the n naught. Okay.
Okay.
All right. Okay, so I think that's it for today. Okay, so okay, I have some questions. Student from G1, G3 form group together. Okay, like for me myself, I like to constrain it to tutorial groups, because later on when we do it's easy for me to manage in terms of like doing the evaluation. So normally I try to make sure that the group is formed within the tutorial group itself, so you cannot cross group. I would recommend not to. I strongly prefer. I don't know whether I'm going to allow it, because from my experience, I never do that before, but from experience from other lecturer, when they have a cross group, it's very difficult for them to manage the evaluation. Like like sometimes they don't have mutual time. So if you are in the same tutorial group, it's definitely you can can just use the tutorial session for the evaluation. So those are some of the concern for having like cross groups. So I would want to restrict it to same group members when you form the group. Okay. Anything else? Oh my god, I'm so sorry. We sort of like extra 5 minutes. So yeah, hopefully we are not going to do this again.
Doctor, I have a question.
Yeah.
So given that the content for algorithms, especially from the book itself, is quite overwhelming and very in-depth, how would you recommend like we go about it and in terms of studying?
In terms of studying, I totally recommend you to I always tell my student, if you want to look into a certain algorithm, try to find the simplest explanation first. Okay, get the concept of what is actually happening. So sometimes you can go to YouTube, try to find a very short video just explaining you like the how do you call that? What is the basic step of that algorithm? So I guess from there on, once you get to understand how does the algorithm actually works, and then you can look into like a more bigger example, and then maybe you can start read the common book, and then you will see what does it mean by like when they indicate about when they talk about what is the especially normally they talk about what is the worst case, what is the worst running time for some function. So I would suggest you whatever it is, whenever you are encountering any algorithm or you want to learn some concept, go into YouTube, find the simplest, most shortest video that you can find, just to get the feeling of what it is the algorithm is about. And then after that you can gradually read about, and then perhaps you can sort of like link it to whatever that you're going to read subsequently after that. Is that all right?
All right, got it. Thank you so much.
Yeah, because the book is very very thick.
It's 1,000+ pages.
I don't think I'm going to recommend you to actually read the book directly. Normally, I would suggest you to go and like even for me myself, normally I would just when I started reading this book, normally I would just go for look for a short the most simplest video, and then after that it makes it easier for you to follow through the book, because the book is very formal. There's a lot of formal definition, mathematics that they use to analyze the algorithm. In our course, we are not really going to like really in depth, but at least when you read the book, you know what it is talking about. So that is what basically the aim of this course. Is that all right? Okay.
Yep, got it.
All right.
Thank you, Doctor.
Okay, so if you don't have any more question, or if you have any more question, maybe you can send me a message through Teams or through Telegrams. Okay. All right. So I'll see you in tutorial on Thursday. Okay. Try to do the question, and then maybe we can try to discuss during that time. Is that all right?
Okay.
Thank you,
Okay.
Doctor.
Yeah. So. Yeah, thank you everyone. Let's have fun. We have another 13 more weeks to go for this course. Okay.
Thank you,
see
Doctor.
Bye. Assalamualaikum. Bye.
Waalaikumsalam.
Thank you, Doctor.
Thank you, Doctor.
Thank you everyone.
Thank you.